Okay. So in the last class we were looking at the reason to go for differential signaling, and the motivations were quite simple. So if we have differential signals, we saw that it is highly immune to any kind of disturbances or on supply and ground, and if done properly it is also immune to interferences. And on top of it, if you realize it as a fully differential circuit instead of a pseudo differential system like this, you also get good common mode rejection ratio. But the problem was that if you have a fully differential op amp, there is high possibility that the output common mode might not be defined. But we also recollected that a similar scenario happened in our two-stage single-ended output op amp, but there the overall DC negative feedback took care of it. But the main difference there is that in the earlier scenario we had only one voltage to worry about, that is one virtual ground voltage or one output. So one feedback loop was sufficient to take care. Here I have two voltages, two virtual ground voltages and two output voltages. So technically I need two feedback loops, and the existing resistive feedback we have that works only on the differential signals. So we saw that we need to have an additional feedback working on the common mode signals, and that's what we call as the common mode feedback loop, and that's what we'll start looking at today. Right? So in case it is still not clear why we do not need a CMFB here but only need CMFB here, no need to worry, let's look at it in detail. So let me first draw the schematic first. So this is the fully differential op amp we have. So let us say I apply bias voltages VCM, and this is connected to some voltage VB. So I am hoping that everyone is convinced that the drain voltages here will not be defined properly, right? And why is it not getting defined properly? Yeah, as we saw earlier, we have two current sources, one PMOS and one NMOS. Both of them are biased independently, and we saw it before also. Even if magically we have the two current sources to have equal value, even then this intermediate node is not defined. And in practice, if there is a mismatch in the current values, this node voltage will keep rising or falling, taking the transistors out of saturation. So here of course the voltages will be set to some value, but it might not be suitable for both the transistors to be in saturation. That's a problem. And what is the fix for this? What should we do? Should have only one current source biased independently, bias the other current source using feedback, right? You guys did it in your midsem also. So first let's look at our two-stage single-ended output op amp. There also we had the same setup. So let us say this is the first stage there, and the second stage was the common source. So even here I have, as of now, two current sources biased independently, but there we saw that if we put this in overall some feedback loop, things started to work. So let's see why that happened. So I'll put it in a resistive feedback like this. So let's say this is connected to VCM. So once I do this, are both the current sources biased independently? Which one is biased independently now? NMOS or PMOS? NMOS is biased independently, this is set independently, whereas the feedback loop is setting the bias voltage here. So things are taken care of. So let's see what will happen at circuit level when we try to form the same inverting amplifier in our fully differential op amp. So here, if I call this as the plus, this is going to be the inverting terminal. So I'll have to connect the resistor like this, same at the other end also, right? This is what I'll do. So even if I form this inverting amplifier with the resistive feedback, is the bias voltage for one of the transistors getting defined by the feedback? I mean, even after forming the feedback, do you think both current sources are independent or one of them is dependent? Both are independent. Both bias voltages are free for you to connect anywhere you want. It is still not solving our problem, right? Because our problem was the fact that the two current sources are biased independently, right? So even now you still have the same problem, which means this alone will not be sufficient. So we still have to do something to make sure that the output is set properly. Right? So we need to have this additional common mode feedback loop, whose job is simple. We need to first sense the common mode of the output. So let me write it here. So we need to sense the output common mode, and let us say you want it to be set to some particular value. So I'll compare it with some reference voltage that is available. I'll call it some DCM ref. Now I have two current sources. I'll make only one of them biased independently and tune the other current source based on the independent, right? So that's what I'll do. So then I can have two possibilities here. So either I can fix the NMOS current as the independent one and tune the PMOS current, or vice versa, right? Either of them is fine. I can fix the PMOS to be the independently biased current source, and I can go and tune the NMOS current so that the output common mode is defined to what value you want, and the currents will also become equal. This is fine. So this is what the solution is in words. Now the job is to translate this from English to circuits, and that's something we can do easily. So let's see. Let me just copy this. So again, I'll just take the diff amp alone. I'll erase the rest of this. Okay. So now remember that when this differential amplifier is operational, one side output, let's say I call this the positive output terminal. So this will be at VOCM plus the half the output. If I call this the negative side, this will be at VOCM minus the differential output by 2. Fine. Now our job is to go and sense the DC bias or the output common mode. I have access to only these two voltages. From this, how will I get the common mode? From these two voltages, how can I extract the common mode? If I add the two, what do I get? But I want only VOCM. What should I do? Average. I mean, that's the definition of common mode, right? I mean, common mode is just the average. So I'll erase this. So now you guys know what to do. So all I need to do is the following. I take the two voltages and I'll take the average. That's clear. But if I say I'm taking the average, it sounds very simple. So as engineers, we should not sound so simple. We'll make it look complicated. So we'll say that we are finding the common mode, or even better, I will say that I am detecting the common mode. So we'll call this the common mode detector. So this will give me the output common mode. So I have done the first part. I have sensed the output common mode. Second step is to compare it with a reference voltage we have. Let us say you are given some reference voltage, VCM ref. So let's say this is VCM ref, and let us say you have a supply of 0 to VDD. What might be a reasonable value do you think we can choose for this output common mode? VDD by 2, because if you choose the bias voltage to be at VDD by 2, then the differential swings can swing symmetrically on both positive and negative side. Right? So typically we do this, but it is not necessary that we should always do this. But it's a reasonable choice. So let us say this is some reference voltage, could be VDD by 2 or anything. Now I have to compare the two. So let us say there is some block here that does the comparison. And then my job is to fix one current source to be independent and tune the other, right? So let us say I'll start with saying that the NMOS is biased independently. So I'll not touch the gate voltage for this. I'll tune the PMOS current source. How will I change the PMOS current source? VB. So this loop should go and control VB finally. Right? That's fine. So finally, if things are all working, what can you say about VOCM? What will it be equal to? If things work as we expected, what will VOCM be equal to? VCM ref. So what can you say about this difference? That difference is 0. But this is the bias voltage VB. That obviously is not 0. So I mean, loosely speaking, I have a 0 input, non-zero output. What is the gain? What gives an infinite gain? So what should I put here? So I'll go and put an opamp here. So what is the missing thing for the opamp now? The signs of the opamp. So let's see, how do you find the signs of the opamp? How will you find it? I mean, but I break the loop, but before that should I do something else? I mean, okay, I break the loop, then what do you do? Okay, I increase, let us say, this VOCM, then I mean, first you have to assume some terminals, right? I mean, let's assume this, that's the first thing, you assume something and go on, right? Otherwise you can't proceed, right? So yeah, so then you increases, so what will happen to the output here? That will increase, so that increases the bias voltage VB. Then what will happen to these two voltages? Decrease. I mean, the gate voltage increases, the current will reduce. I'm pushing in lesser and lesser current, so the node voltages will start to increase. Sorry, would start to decrease. So both of them decreases. What will happen to the common mode? So is it in negative or positive feedback? So assume signs are fine. So I'll freeze that as the final signs. So I'll erase all these arrows. So this is one, or I would say this is a very generic implementation of the common mode feedback loop. So in particular, I'll call this common mode feedback variant P, where I'll say that P denotes to say that we are tuning the PMOS current. That is just notation I'm following for the class alone, not a general thing. Great. So now let's see how we can implement everything on circuits. So first let's look at the detective block, common mode detector, and this common mode detector is just taking the average of two voltages. If I have two voltages, what is the easiest way to take the average? They put two resistors of equal value, the midpoint will be average of the two, simple. So that's all. This guy is not so complicated. Oops, it is just two resistors. So I'll just put two resistors like this with equal value. I'll call it RCM and RCM to denote that they are for common mode, and I'll go and connect it here. So this guy is not drawing any current, so this voltage is the average, nothing will change. So one simplest realization of the common mode feedback is this, right? So let us say I find that the output common mode is increasing. If the output common mode is increasing, do you think the PMOS current is greater than the NMOS current or the other way around? When I say the common mode is increasing, the drain voltage here is increasing, let us say. So which means, do you think the PMOS current is greater or the NMOS current is greater? PMOS. As a corrective action, what should I do? Decrease the PMOS current, right? which means what should I do to the gate voltage of the PMOS? I should increase it. I mean, that's what is happening. It's connected to the positive terminal. But see, you see that if this increases, you should go and increase this. What is the simplest connection you can make? You can directly short them, right? So that's what you can say, that I will not do anything. If you say that I hate op amps, I don't want to use op amps, not a problem. But of course, you should not be saying you hate op amps. It's okay. So you don't need to use this. This is the simplest connection you can make. Fine. Let's see if it works, right? I mean, at least there is definitely a feedback here, right? Feedback is negative. So it is not like the two current sources are independently biased. That much is clear. This I'll call CMFB variant P1, the first thing. And let's actually draw this in a more aesthetically pleasing fashion. Maybe I'll just copy paste the entire thing. So if I look at the circuit, what we are doing is the following. I have the two resistors connected at the two outputs, and the sensed common mode is directly connected to the bias voltage. So I'll redraw this nicely. So what I am doing is this: I am taking the two resistors like this, RCM and RCM, and I am going in connecting it like this. That's it. This is what I've done. Great. So let us say now I apply the bias voltages at the gates. Now tell me, what is the voltage to which the output common mode is getting set to? What is the DC potential here? Okay, these are the two voltages. Where is the common mode obtained here? Huh? And what is it connected to? Now, if the feedback is working fine, what can you say about the currents in the PMOS and NMOS transistors? Which means, what is the current flowing in the PMOS transistor? I0 by 2. If the current is I0 by 2, I know we have feedback setting the gate voltage. What will the voltage be? So what is the output common mode? Is it clear? The output common mode is the average of the two, same as your gate voltage for the PMOS. So this will get set to VDD minus VSG of the PMOS at a current of I0 by 2. Right? If it is not clear, we can look at it this way. So let's actually see. I mean, we are now interested in common mode behavior, right? Both inputs are same, common mode excitation. If I have common mode excitation, what can you say about these two potentials? They will be equal. So if the moment I find two nodes with equal potential, what do? I'll go and short. If I short these two, so things get put in parallel, we can reduce it. So let me draw the common mode half circuit now. So first let me draw the main NMOS and PMOS. So this is the PMOS. We have 2x of them put in parallel. I have the NMOS also. Two x of the NMOS put in parallel, and then I have the tail current source biased with current I0. Now at the output I have a resistor RCM. Again, when I fold the two resistors get put in parallel. Okay, so this becomes RCM by 2. I am shorting these two, which means the two resistors are put in parallel, RCM by 2, and the other end of the resistor is connected to the gate of the PMOS. That's it. again, one thing to notice, the circuit I am drawing is the common mode half circuit. That is, even for DC this is valid. This is not the small signal half circuit. This is the complete common mode half circuit. Even for DC you can use it, right? Okay. So now we can clearly see, if I look at this potential, the output common mode, that is same as your gate voltage. That is what it is getting set to. Now on top of it, let us say here I have a small signal VIC getting added. Now we can use your small signal analysis and find it, and this is something you might have calculated multiple times. So you can find the small signal common mode gain. I'll give it as an exercise for you to work out. And ideally the common mode gain, you want it to be very small or very large? Very small, right? And you can work out and see it will be small. Okay, so remember that this common mode business is just, this is not our main, common mode is not our main business. Our main business is to make an op-amp with a large differential gain. This additional common mode, this is all, side business, bells and whistles that we are adding to keep all transistors at saturation. So let's not deviate, and let's verify that differential mode gain is fine. For that, let's assume that I apply a small signal differential signals plus VID by 2 minus VID by 2. If I apply differential mode signals, what can I say? Can I reduce the circuit now? Yeah, how will you do it? All the nodes along the line of symmetry, they will be at small signal ground. So that reduces. So let's quickly draw that, the differential mode half circuit. And again, remember, when I draw the differential mode half circuit, this is the small signal half circuit. Okay. Because when I apply differential mode signals, they are all small signals, and even the fact that the nodes along this line of symmetry being incrementally short works only for linear networks, right? Only for small signals this is linear. So this is incremental differential mode half circuit. So if I draw it, so I'll just draw the PMOS and NMOS first. So this is the PMOS and NMOS, done. I apply plus VID by 2, and I can call this as the positive output, VOP as plus VO by 2. Now the gate voltage is incrementally short, that's along the line of symmetry. So gate of the PMOS is incrementally short, and you look at the common mode detecting resistor that is connected from the output to small signal differential ground. So I'll have the RCM connected like this. This is fine. Half circuit is fine. So yeah, now tell me, what is the differential mode gain now? Differential mode gain is the gain VO by 2 by VID by 2. That is same as VO by VID. What is it? Very good, minus GMN times. Yeah, R0 and parallel R0T in parallel with RCM. Great. That's all. Now if you want to make sure that whatever you are doing for the common mode part is not affecting your differential mode gain, what is the condition you see from this? RCM should be much greater than your intrinsic output resistance, that is R0 and parallel R0, right? That is something you have to choose, because remember, our main business is making an op-amp with a large differential mode gain. No one cares about the common mode, right? That is for you to take care of. So in that process of taking care of common mode, you make sure that you don't affect your differential mode performance. Good. So this is one simple variant of common mode feedback. But here the issue is this: the output common mode is getting set to a proper value, VDD minus VSG, but this is not completely under your control, right? Because VSG will depend on threshold voltage, the mobility, and these things can vary a lot. So to get a better control, or to exercise a better control on the output common mode, you cannot use this. You have to use the op-amp, right? No escape from the op-amp, you have to use this fellow. So now let's see how will that look like? So I'll call this the variant 2 and using the opamp now. Cool. So now we have to replace this fellow. I need to have an op-amp or a block that takes in 2 inputs, gives single-ended output. What is the simplest candidate that you know? The 5 transistor OTA. So let's replace it with the 5 transistor OTA. So we'll actually keep it aside so that we know what to do here. And I'll draw the 5 transistor OTA first. So this is the so let's say it's biased with some current Ix. This is the OTA, and I know for sure that this is the output, right? The right side here is the output. So here tell me which is the positive terminal, the left side or the right side? Left. Remember that if I increase the gate voltage here, what can you say about the drain voltage? Decreases. So right side is negative, right? So that should be clear. This is positive. So let's look at the connection we have. We are connecting the sensed output common mode to the positive terminal. This output of the resistive divider is the sensed output common mode. So I'll actually go and connect it to the positive terminal. Like this. At the negative terminal, I connect the reference voltage VCM ref, and the PMOS is biased with the output of the first output of this OTA. This forms the full circuit. So I'll erase this. This is fine. So here when I do this, I expect that the output common mode will be set to the reference VCM that you are providing. That's the expectation, but let's verify if that is the case. And for that, let's draw the common mode half circuit. Again, the complete common mode half circuit, not the small signal version. So again, for common mode signals where I apply the same DC potential VCM here, both sides are equal, so you can short things. So I'll directly draw it. So things will get put in parallel. So I have only one NMOS. 2x of the NMOS will be there. Fine. Similarly, I have the PMOS folded, so I have 2x of the PMOS. Right. So I'm just directly drawing. Let me know if it's confusing. And the two resistors will also get put in parallel. So that becomes RCM by 2. I'll remove this. That's it. This is how the common mode half circuit will look like. Okay. This is fine. So now look at this common mode half circuit and tell me if this resembles something that you have already seen. Folded cascode. Why folded cascode? Remember that I have a 5 transistor OTA. Yeah, the output of this goes to gate of a PMOS and we are tapping the final output from the drain. It's a 2-stage OTA that we have seen, right? So if I were to sketch it at a block level, what I have is this. The blue portion is the 5 transistor OTA, the first stage of the first stage of the 2-stage OTA. This is the first stage. The output of the first stage is going and feeding to the gate of the PMOS. That is the second stage. So that is the second stage. from the output of the PMOS, that is the output of the second stage, I have a resistor RCM by 2 connected. So let me draw that resistor first. RCM by 2. Other end of the resistor is connected to the positive terminal of the first stage. Other end should be connected to the positive terminal. Is the connection fine? Here is where I have VCM ref. So I have just sketched the same thing at a block level, right? So I now have a two-stage OTA like this put in feedback. So any comments?
So is it for small signal or
this is for the complete picture, right? Even for small signal, this is the case.
so the second stage OTA has a positive terminal grounded, but here we have VIC.
Second stage is positive terminal grounded. I didn't understand.
In the second stage of the OTA.
Oh, okay. Oh, yeah, fine. Okay, fine. I mean, yeah, fine. Connected to this one you are saying, right? Let's say that's okay. Let's say this is only for small signal. That's also fine. But yeah, let us say now we have two-stage OTA put in feedback. Any comments now? Huh? Should I let it be like this, or should I do something to make things work? I mean, two-stage op-amp, when you put it in feedback without doing anything, what do you expect? Will it be stable? Might not be stable, so you have to compensate it. What is the simplest way to compensate this? Where do I put the Miller cap? Second stage, which is this fellow. So I'll go and put a capacitor here. I'll call this the capacitor CCM. Compensation for the common mode. So here, this is the second stage. I should put the capacitor from the input to the output of the second stage here. Fine. So I'll go and put the capacitor. So this is in the common mode half circuit. The capacitor should get put across the 2 times PMOS. Now in the actual circuit where I have 2 PMOS transistors, how will the capacitor come now? In the half circuit, what I am saying is I have a single capacitor CCM put across the 2 PMOS in parallel. In the actual circuit, how will the capacitor be put now? You have to put 2 capacitors. What value? Double or half? Half, right? So let me just put that. So here I should go and put a capacitor with half the value. See, that's it. Because then if you fold this two and put in parallel, CCM by 2 times of it comes in parallel to get CC. So here there might be a point of confusion. So just want to clarify that the actual amplifier that we are making, the differential amplifier that we are making, that is still a single stage OTA. This is a single stage amplifier, right? Now in order to set the output common mode of this single stage fully differential amplifier, we need to have an additional amplifier, and with respect to the common mode signals, this entire combo looks like a 2-stage OTA. Only for the common mode signals, this is like a 2-stage OTA, but for differential mode signal, you only have this part active. We'll also confirm that, but this is the main differential amplifier, single stage amplifier. To set the output common mode of this single stage amplifier, we are requiring an additional amplifier, and that is active and participating only for common mode signals. So only for common mode signals, we have this 2-stage behavior. Okay. So if you don't compensate this CCM by putting CCM here, what will happen is this: anytime you see a common mode change in your amplifier, the common mode loop you see is not stable because you have not put the capacitor. So the common mode signals, we will see a lot of ringing and instability. Okay. But of course, if you take the differential thing, it might be fine. But the common mode signals will see a lot of ringing and instability. Okay. So we have to compensate, and this compensation is done for the common mode loop. Differential mode is still single stage. Is that clear? Okay, so this is the complete circuit. So there are a couple of things that we might do in practice in addition to this. So let me put this common mode picture here. This is the common mode equivalent. So remember, we discussed the following while looking at two-stage OTAs. So let us say you design this loop so that you have good phase margin. Now remember, in practice we'll have a parasitic capacitor here at the gate. Let us say you didn't account for this parasitic capacitor while designing. So this will introduce an additional pole and degrade the phase margin. What was one quick fix to counter this? I mean, one solution is to account for this while designing and kind of, do things. But let us say you didn't do. Now we want to do a quick patchwork and make the things work better. So what can I change here? Okay, remember that when I didn't have the capacitor, any change I make here instantaneously appears here, right? Because here there is nothing, open circuit. But now with the capacitor, there will be a delay in this path. Now if you want to counter this delay, what can you do? Add a 0 or a faster path. How can I add a 0 in this RC circuit? Capacitor where? Across the resistor. Fine. Please recollect, we discussed this while discussing the two-stage Miller compensated op amp also. So you can put a additional capacitor. I'll call it CMZ to denote it is for 0. So now anytime you see a change at the output, now this capacitive path will be active. This capacitor will provide the faster path and make sure that we have a capacitive division, so things get fed back instantly, right? Otherwise you will have a delay through this RC. Okay. So that capacitor also we can add. So we have to add this capacitor here. So let me add it somewhere here. So this is CCM Z by 2, and RC. Okay. Cool. So now couple of questions to you. See here, all I knew was I wanted to use an op amp, but I have used an NMOS input op amp. Do you think a PMOS input pair would have been a better choice here? Is my question clear? We started off with the fact that we wanted to have an op amp, wherever it is, op amp here, and that op amp, as of now I have realized, using an NMOS input differential pair. Could I have done better with a PMOS input pair or no?
Depends on the VOCM value.
Yeah, so depends on VOCM value. VOCM is VDD by 2, let us say. So both NMOS and PMOS might work fine. Depends on? Why?
Because that is VDD minus VSD, and again the same potential.
Yeah, remember, if you look at the common mode half circuit, it becomes clear. This is the common mode half circuit, right? So my second stage is a PMOS stage, which means my first stage is better off with an NMOS. We saw this even for two-stage op amp, right? Remember that with respect to small signals, there is no difference in using an NMOS input or a PMOS input. If at all there is any difference, it is in the DC potential. Now remember that if I use an NMOS input pair here, so let us say I call this potential, nominally what will this potential be at DC potential? VDD minus VSG of the PMOS transistor at what current? I mean, this is, I'll call it IX, okay? Ix by 2. Now this potential, you see, it is the gate voltage of this PMOS. What will that be set to? VDD minus VSG of that PMOS. I'll call it, I don't know, to make distinction, I'll call it VDD minus VSG P2 at a current of. So now you see that naturally the first stage is providing a voltage that is more compatible for this structure. On the contrary, if I went and tuned the NMOS inputs, NMOS current sources bias voltage, then you will find that using a PMOS input pair is better. The same considerations you will have while designing a two-stage OTA, right? If your first stage is NMOS, you saw PMOS as a second stage is better. Similarly, if this connects to the NMOS, that is the second stage, if it is NMOS, then having a PMOS input as the first stage is better. Okay. So then one other point to take care is this. See here, this drain potential is at VDD minus VSG of this PMOS transistor. This drain potential is at VDD minus VSG of these PMOS transistors. If I don't choose the two VSGs to be equal, then the two drain potentials will not be equal. If the two drain potentials are not equal, what can you say about the gate potentials? They will also be not equal. So which means the output common mode will not be exactly equal to VCM ref. It will be VCM ref plus some offset. Right? This is something we saw already. This is what we defined as what? Systematic offset. If you don't want to have this, what is the simplest fix? Current and that we at the end we should have the same VSG. As a designer, it boils down to the fact that you use the same current density and same length for all the PMOS transistors here. That is, all the PMOS transistors must have the same lookup table parameter. So I will say it is same length and current density. Remember that if I fix the length and one of the lookup table parameters, everything else is frozen, and this is what I should do. And this should be a typical design choice you make while designing a two-stage or a three-stage op-amp, right? Great. So cool. So now we have seen what happens with the common mode picture, and we saw that for common mode signals we need to stabilize it and take care of the sizing properly. Then the output common mode will hopefully be set to the applied VCM ref. Common mode is fine. But again, let's not deviate ourselves. Our main job is to make a differential amplifier. So let's actually see what is happening to the differential mode gain. I'll just again take this. Oops, don't have this. Okay. So let me erase this. Erase all this now. Okay, so now let us assume that we are applying a small signal differential mode signal. So on top of VCM, I am applying small VID by 2 and here minus VID by 2. So once again, you guys know all the node voltages along this line of symmetry, they will be at small signal ground. So which means this is at small signal ground. This is at small signal ground. If the gate potential is at small signal ground, the output of this op-amp is also at small signal ground. Now this is the constant DC voltage for small signals. What will this be? That is also small signal ground. Then, and if you carefully notice, even this is at along the line of symmetry, right? Although I have flipped it horizontally, this is also along the line of symmetry. Can you see this? So even this will be small signal ground. I mean, this is not very visually understandable, remember that for differential signals, these two will be, if this is plus V by 2, this is minus V by 2. So I take the common mode, that's 0. So now we can nicely simplify it. Now you see that for this op amp, the inputs are grounded, output is grounded. This is not at all present in the differential mode picture, which is good because you don't want a lot of interference from the common mode in the differential circuit. So let me get rid of this. So this is gone, so I'll erase it. Right. So now let's actually draw the differential mode half circuit neatly. This is differential mode half circuit, but small signal equivalent, okay, incremental equivalent. So first I'll just draw the PMOS and NMOS, the main things. PMOS source is grounded. This is the main part of your differential amplifier. Let us say I apply plus VID by 2 and call the output VOP as plus VO by 2. This much is the bare minimum. Now let us see what portions of your common mode feedback loop is present here. So what can you say about this capacitor CCM by 2? It is connected plus it's connected from the output to small signal ground. So it is going to come here, and the gate voltage of the PMOS transistor is small signal ground, right? So that also I'll go on short here, right? And then you have these two fellows. What can you say about these two? They are also connected from the output. Other end is small signal ground. Right? So first I'll draw the capacitor. So this is CCMZ by 2, and then I have RC. Fine. So what is the differential mode DC gain now? Again minus GMN. This is only the DC gain. Same, right? R0N parallel R0P. So again you have to make sure that the common mode detecting resistor is much greater than the existing output resistance, so that it doesn't affect you. But also you see that now because of the CMFB we are using, we have these capacitors, and these capacitors are compensation capacitors we are using to stabilize a common mode feedback loop. We are actually loading your differential mode circuit also, so this will impact your pole locations, unity loop gain frequency, blah blah blah. But anyways, this is a single stage OTA. Can you tell me what is the unity gain frequency of this? GM? For it's a single stage, it is a first order system or a second order system here? Unity gain frequency, how will you find? Yeah, well, let's say for a first order system, I give a transfer function. What is the unity gain frequency? How will you find? Open loop pole, is that it? DC gain times pole. DC gain is GM times R0. Pole is 1 by R0 times C. So effective is GM by C, right? So it is GM of which transistor here? And what is the capacitance you have? So CCM plus CCM C, right? So this will be your unity gain frequency in this. So you see that this is going to directly impact your unity gain frequency in your differential mode, right? So you can't go crazy. I mean, remember that to stabilize any feedback loop, I can go and put a large capacitor so that pole splitting happens nicely, things are stable. But if you go and put a large CCM capacitor in the with the aim of stabilizing your common mode loop, now you see that it is impacting the unity gain frequency of your differential circuit. So we have to design it carefully. Let's stop here and